So in the first clip in this sequence, we looked at surface integrals of scalar fields. Now we're going to look at surface integrals of vector fields. And a standard application of this is to compute the flux across an oriented surface of some kind of vector field. And we want the component that's orthogonal to the surface, and I'll talk a bit more about that in a moment. But to begin with, the setup that we have is we're just going to be looking at what is actually a scalar integral. I mean, I've got a vector field in here, capital F, so you're like, what are you talking about? But look, this quantity in here, in the green parentheses, this is a scalar because after you take the dot product of one vector with another vector, you get a scalar, right? In fact, the dot product is sometimes even called scalar product. So this is actually set up as the integral of a scalar field over a surface. And so this is how you should understand the meaning of a flux integral. Or more generally, the integral of a vector field over a surface. So let's see. So now if we set this up in terms of a parametrization, then it's going to be the integral over the parameter domain of, and then we'll have f dotted with, and then we look at the unit normal we get from the parametrization. So that's going to be sigma u cross sigma v. That'll be orthogonal to the surface. And then we have to divide by its magnitude in order to get something that's of unit length, right? And then this is going to be multiplied by ds, which is the magnitude of sigma u cross sigma v dA. And just like we've seen before, Shazam, we get cancellation. And that leads to the double integral over the parameter domain of f dotted with sigma u cross sigma v dA. And so this is actually, so this is how we compute a flux integral. Or more generally, how we compute the surface integral of a vector field over a parametrized surface. And then for short, we write it just like we've seen before. So this is going to be the integral, whoops, now back over S of f dot d sigma. And so this is notation, or how we write a flux integral. Okay, and so then compare this to what we've seen before, right? So earlier when we were looking at flux integral, we said we were doing it one dimension down. So we were looking at it, the integral through a curve f dot n d little s, where little s was the arc length element. And then in terms of the parameter domain, this is going to be the integral over d of, and then f was given by components p and q, and this was going to be dot with, and now let's see what's going on here. So in order to set this up, we will need to give a parametrization for our curve. So we'll just call those components x and y, and then c prime is going to be x prime, y prime. And then for a normal vector, we're going to need, well, how do you find a vector that's orthogonal to a given vector? The easiest thing is to interchange the positions of the components and make one of them negative. So we'll go y prime minus x prime, right? This is the same thing that you learned back in grade 8 about how to find the slope of a line that's orthogonal, right? If your line is y equals mx plus b, then the orthogonal one has slope minus 1 over m. That's just what I did, that minus 1 over m. So the 1 over part, that's swapping them, and then the minus, well, that's the negative sign. Okay, so we've got this guy, and then to make it a unit vector, we're going to have to normalize, so divide by the magnitude, and that's actually the same thing as the magnitude of c prime, right? So we've got y prime minus x prime divided by the magnitude of c prime. And then we have ds, which is c prime dt. And so beautiful little cancellation, and we end up with the integral over d of p y prime minus q x prime dt, which we typically just write in differential form as p dy minus q dx, right? So this is just sort of a recap of what we did before, but in a slightly different order and perspective. So just like when we did the flux integral around the boundary of a region in Green's theorem, so this is f dot n d little s, this is going to be the double integral over the enclosed region of the divergence of f dA, right? So that's what it looked like when we connected a one-dimensional integral around the boundary with a two-dimensional integral across the interior of the region. We'll see in our very last section, 16.9, the divergence theorem, sometimes also called Gauss's theorem. We will see that if we take the flux integral over a closed surface, and now we get a circle in the double integral, of some solid region E in R3, then f dot n with respect to surface is going to be equal to the triple integral over the region E of the divergence of f with respect to the volume set up in some set of coordinates. So earlier we only ever talked about the flux integral, by the way, in the context of it being a closed curve. Flux integrals make sense for non-closed curves as well. They just don't have a natural notion of orientation, so you have to specify it. But you could say, if you have, say you're doing an application, you've got some stream, and f is giving you water velocity, and your surface is going to be as seen from the top. So here's some, here I can try and draw it in 3D to make it look like spiffy. Okay. Maybe I shouldn't have. Okay. But here's some surface. Yeah, I should have quit while I was ahead. Think of it as a screen, and so think of it as like, okay, so we've got water is rushing through, coming down the stream here. It's moving faster at the center and slower at the sides, and maybe whatever else. Then if you want to find out like the volume of water that's passing through some region per unit time, you're going to take the integral of the flux over that kind of region. The other thing is, and this is going back to what I said before about you want to get the part that's orthogonal to the screen. Imagine your screen looks like this, right? And we've got water flowing slowly. And I'm not gonna, like I said, embarrass myself by trying to draw this one in 3D. Now look what's happening. If you're trying to measure how much fluid is flowing across the screen, well, right here it's actually moving parallel to the screen. It's not crossing the screen at all. Now here it's crossing. It's going transversely through it, and here as well. And here it's going partly transversely through and partly along. And so the thing that you want to get is you want to say, okay, let's look for fluid moving through here. Let's compare that to the normal vector and look at that component, that normal component. And you find out, oh, okay, that's an idea then of how much is passing through directly. So that projection onto the normal vector, as we get to a point over here, the projection of the purple one onto the red one is 0. If we're over here, the projection of the purple one onto the red one is, it's completely on the red one. So anyway, so that's why we have the dot product, and that's why we want to take only the normal component.